Thermal physics, so we'll just have a look at our thermal physics concepts. Okay, we've got equations for heat, energy, and also some equations for our ideal gas. These are the ones that we're looking at in this question. Sample of vegetable oil, which is in the liquid state, is placed in a freezer and transferring thermal energy. And we're being asked to show how we're looking at how the temperature varies. Okay, we're told the mass of the sample, we're told the rate of heat fusion, and the rate of energy transfer. First one, calculate the energy transfer from the sample during the first 30 minutes. Now, just a key point here, you notice here this graph is deliberately divided in half. We've got a time from 0 to 30 and a time from 30 to 60. Okay, because we are using a constant rate of energy thermal transfer, any energy that's transferred here is going to be the same as the energy transferred here, and we'll use that in a later part of the question. Okay, ignore this bit for now. I got a little bit distracted. This question is actually very, very simple. All we have to do is think about our energy transfer. Okay, we know the power of our heater. We also know the time. The thing that we have to be careful with is turning our time, 30 minutes, into seconds simply by multiplying. We're going to do 15 watts times 1,800, and we end up with 2,700 joules. So during this portion here, we're going to have 2,700. My apologies, 27,000. Okay, but also here, we're going to have the same amount of energy transferred, also 27,000, and that's what we'll use later on. We're going to estimate the specific heat capacity. Okay, we think about what we know here. We know the mass, which is 0.32 kilograms. We want to know C. We know Q, which was from the previous question, and we know delta T. We don't know delta T simply by looking at the graph, which is our 290 take away 250, which is going to be 40 Kelvin. Okay, then we take our energy, divide by those two numbers to get our specific heat capacity, and then we're asked for an appropriate unit for our answer. Well, specific heat capacity is the energy per unit mass per degree of temperature change, in this case Kelvin, and so therefore you have joules per kilogram per Kelvin. You could, if you wanted to, put in per degree Celsius as well here. There's no problem with that because a change of 1 degree Celsius is the same as change of 1 degree Kelvin. We're then asked, the sample begins to freeze during the thermal energy transfer. Explain in terms of the molecular model why the temperature remains constant. Okay, well, we should, for this one we need a kind of fairly general response. We need to understand that during freezing, the particles become closer together and they form bonds. Now, I find this really interesting. In the mark scheme for this question, they're very keen on hearing this word bonds. Now, in my opinion, bonds is very much a chemistry kind of concept, and we tend to talk about forces in physics, whereas where a chemist talks about bonds, we talk about forces. However, it's interesting to note that they really wanted this in this particular question, so that might be something to note when writing future answers. When this happens, their potential energy decreases, okay? And this is released as heat energy, okay? We have talked about latent heat, and the idea that even during a state change, we will either gain or lose energy depending on what the state change is. Now, during this process, the average kinetic energy of the particles is unchanged. Now remember, we measure temperature as being essentially a measure of the average kinetic energy of the particles in there. So if you want to explain why temperature is constant, that must mean the kinetic energy is constant, and so therefore the temperature must be unchanged during freezing. And that's really the key point here. You notice here that, I'll be honest, there's a bit of waffle here. We're just sort of discussing what happens with the particles. The potential energy decreases, okay, fine. But the real meat of it is that last sentence there, that the average kinetic energy remains unchanged and therefore the temperature is unchanged. Temperature being an indicator of our kinetic energy from our equation, 3 over 2 kBT is equal to the average kinetic energy. All right, last one. Okay, we're asked to calculate the mass of oil that remains unfrozen. Okay, now, key point here being that we're going to use our Q equal to delta ml. Okay, delta M being the energy divided by our specific latent heat, and this is where we need to make use of the fact that they've chosen those nice numbers, 30 and 30. Okay, remembering that 27,000 joules came out here, 27,000 joules come out here as well. So we can use in those 30 minutes that energy supply, or that energy loss, I should say, divided by the L, and we end up with a value here of 0.21. Now, what is that 0.21? 0.21 is the amount of mass which has undergone a state change. Okay, so in this case, we're freezing, we're going from liquid to solid. That means 0.21 kilograms have become frozen at this time. So in order to find the amount that is unfrozen, we're going to have to take the mass and take away anything remaining, and therefore we're left with 0.11. So this is a key thing about reading the question. You need to very carefully understand what the examiner is asking. In this case, we're not looking at the mass which has been which has frozen. We're actually looking at the remaining mass. Okay, make sure you have a look at those, check your answers, ask any questions, and get ready to move on.